Alright, so that's section 9.6, conic sections in polar coordinates. First of all, let me apologize for bringing this up so late. I forgot that I hadn't done this. I thought that I had. I have another class, but the two classes are slightly shifted, and I thought I had recorded both, but apparently I hadn't. And one student reminded me today, called my attention for it, so I apologize one more time. Thank you for that, student, for letting me know that I had missed this video. So I'll record this real quick. I'll upload this today, and we should be able to complete all assignments that you need. Okay, so what we're seeing now is an alternative way to represent conics. So we've seen conics, and again, conics are parabolas, ellipses, and hyperbolas. We've seen them as regular rectangular equations, but now we're going to see them in terms of a focus and a directrix, so that we can write polar equations for them, right? And the principle is the same as before. It's to have polar equations in terms of r and theta that describe either parabolas, ellipses, and hyperbolas. Okay, so let's see exactly how we define them, and that's the main and the key point, I guess, to make this definition or these equations work. So the key concept here is the eccentricity. So this is a word that people are trying to get changed. So far it's still what it is. It's eccentricity, right? We have here three possible values for the eccentricity, and one way to sort of unify all conics is through this equation here. Any point that satisfies, if you have a focus, right? A focus, a point F, and a directrix, which is a line. As long as the distance from the point to the focus divided by the distance from the point to the directrix is some fixed value, you collect all points that satisfy this property, that this division, right, is this fixed value, then that's going to be one of the conics that we know, either a parabola or hyperbola or an ellipse. And then based on the eccentricity, we're going to be able to tell whether that's a parabola, an ellipse, or hyperbola. So I remember this. Remember that we did b squared minus 4ac, right? And if that were less than 0, then that was an ellipse. If that were 0, then that was a parabola. If that was greater than 0, then that was a hyperbola. So the same thing here works. The same thing works here, except that instead of comparing it to 0, you're comparing it to 1, right? So that's what you got to remember. So instead of comparing it to 0, you compare it to 1. If it's less than 1, then it's an ellipse, right? If it's equal to 1, it's a parabola. If it's greater than 1, it's a hyperbola. One way that I like to think about that number too is to think about it as a measure of the weirdness of the conic, if that makes any sense. So an ellipse is a lot less weird than a hyperbola, right? And another important thing, if e equal to 0, right, which is another thing that you can, another case that you can find when you're finding eccentricity through rectangular coordinates, is that this is a circle. So I'll say this, I'll write it out, and maybe you'll see that again in the future. A circle is an ellipse with eccentricity equal to 0. So that's an important piece of knowledge for the future here, which makes sense, right? An ellipse is a weirded out circle, right? You sort of elongate it in one direction, and if you sort of don't have any deformations on the ellipse, then that's just a circle. Okay, anyway, let's keep going. So that's how where the directrix shows up in the parabola. We've talked about this again. This is part of the latus rectum, right, of the parabola. And you just got to remember that the directrix is the same distance from the vertex to the focus, but in the other direction. Okay? I'll erase the line on top, over top of the directrix here, so you can see. So this is the directrix, right? Okay, just got to remember that this distance is the same as this distance. And that's why equals to 1, right? Because this equals to this all the time. So when you have the directrix opposite here, right, this distance is a bit larger. So I have the directrix outside. I mean, you could have it inside too. You could have it here. It's a possibility as well. We're going to discuss that in a second. Okay, but when this is less than 1, right, then we have an ellipse. And when this is greater than 1, then we have like the focus. This is a bit larger than this, right? That's the point. It's just comparing the distances, and that should help you. Okay? So these are the 3 things you have to remember for now. Next thing is how to put this together to find the polar equation of those conics. So first you have to know certain another important quantity. So you have the eccentricity is E. Remember again that E is positive in that case, even though I sort of gave you a hint on E equal to 0, what happens, and I didn't tell how to calculate it when it's a circle, but that's what happens here. And P is going to be the distance between the focus and the directrix. So it's going to be from the focus to the directrix. We always want to have the focus at the pole. Okay, so for polar coordinates, we're not going to shift left or right. We always want to have, the focus at the pole if it's a parabola. If it's an ellipse, we always one of the foci to be here, and if it's a hyperbola, right, we're going to have like here. So we have like 2 foci as well, but only one of them, right, is at the pole. Okay, just gotta remember that. Okay, so here are the 4 possible equations. Very, very easy to remember. Just gotta remember that as well. So it's EP over 1 and plus or minus E times cosine or sine of theta. It's very, very easy to remember. The most important thing is that you have to remember that this term here at the bottom has to be a 1 regardless. Okay, and then depending on whether this is a cosine or a sine, you're going to decide whether you're going to have your major axis horizontal or vertical. So if it's a cosine, it's horizontal. If it's a sine, it's vertical. The way I remember this again is because x is r cosine theta, right, and y is r sine theta. So cosine means x, which is horizontal. Sine means y, which is vertical. That's how I remember this as well. And depending on take a look at that. So the eccentricity is always positive. We always want that, right? Depending on the p-value, then we're going to see where the directrix is if p is positive, right? So let me just be clear on that again. P is what determines the rest. Once you get a 1 here, then you can easily see what's E. E is the thing multiplying the cosine or the sine. And the next thing that you need to do is find the p-value. And the p-value is going to determine, right, whether the directrix is to the right or to the left. So you see x equals to p is here. X equals minus p is there, right? And that's because I have a minus sign over here, right? So you always want that. So if that's a minus sign, then you go to the left. If that's a plus sign, you go to the other side. Okay? So the directrix is always sort of pushing the equation, the graph away. So same thing here. Now it's sine, so it's vertical. So it's either up or down rather than left or right. And because it's a plus, right? The directrix is up, so the curve goes down. And if it's minus, then the directrix is down, so the curve goes up. Okay? So that's how you gotta remember these. It's not that difficult, and these are some instructions on how to graph them. I'll go over the first few steps, and then I'll describe what to do for the third step, and I'm not going to go over it because it's not that difficult. You can also check page 1044 if you want to see some more details on that step. Though it's not that complicated, I'll just make sure that I describe it well. We've done this before, so that third step is not a huge issue. So let's begin by looking at this. So we have a polar equation we're given, and we have to make sure that this is a 1. Okay, so to get a 1 here, we have to divide both the top and the bottom by 2. Right? So divide by that number that's not a 1, and we make it a 1. So r equal to, so we divide that by 2, so zoom in a little bit, and divide that by 2. So 4 divided by 2 is just a 2, 2 divided by 2 is just a 1, and then we have to divide cosine as well, right? That's what we have. Okay? It's the same as multiplying by 1/2, dividing by 2 is. Okay, cool. So now that I have a 1 here, now I can easily see that that's e. Okay, so e equals to 1/2, which is less than 1. Remember, this time, rather than compare it to 0, I'm comparing it to 1. And when it's less than 1, then I see that that's an ellipse. So I'll move on to the next slide, because that's, I think, where I do this. See, so I can easily see that e is 1/2, and that p, so remember, right? The top is EP, so EP equals to 2, and I know e is 1/2, so p equals to 4. P is the distance from the directrix to the focus, or to the pole, right, which is the same. So p equals to 4, e equals to 1/2, because e equals to 1/2 is less than 1. Then this is an ellipse. Because e is less than 1. So now I have a pretty good idea of what to expect. Okay? So how do I know what to expect? I know, let me not do this yet. I know that, let me, my axis here. So because this is a cosine, then my major axis is horizontal. Okay? This means the major axis. Major axis just means the longest axis of the ellipse, right? The ellipse is longer horizontally than vertically. So the ellipse is like this, not like this, right? Now, so the pole is one of the foci, okay? And the distance from the foci, from that focus to the directrix is 4, which is p, and I move negative in the negative direction. So I move to the left because it's horizontal and negative. So I move 4 units there, so that's a -4. So that's where the directrix lives. Okay, that's the directrix. So x equals -4 is the directrix. Okay, now I have the directrix, I have one of the foci, I have the eccentricity. So because I know my ellipse looks like this, okay, so let me go back down. That's what they're telling us. I want to go ahead and find some of the points. So I want to find these 2 points. So I know my ellipse looks a little bit like this, right? So I want to find these 2 vertices here, which are the points on the major axis. And looking at this, right, the argument of here is theta equals to 0, right, in this direction. And the argument here, the angle, is theta equals to pi. So these are the 2 points that I'll plug in first. So this is what they're telling me here, 0 and pi for theta. I'll do that, and I'll find the 2 values. So I'll go ahead and do so theta equals to 0, so I'll go r equal to, I can choose any of the 2 equations that I want, doesn't make a difference. Usually I go with the original ones if the numbers are okay. So I'll go r equals to 1, 2 minus cosine of 0. You don't have to though. Cosine of 0 is 1, remember, so that's 2 minus 1 is a 1. So r equals to 4. So we have a point r theta 4 comma 0. And then, so if I graph it, so it's not x, y, right? Remember, it's r theta this time because it's polar coordinates. So we have a 4 right here in the 0 direction, in the 0 angle. And then theta equals to pi, right? So it's 4 over 2 minus cosine of pi. Let me erase this angle symbol here. So it's, remember the cosine of pi is 180, the cosine is -1, so that's a 2 minus a -1, so that's a 4/3. So we have the point 4/3 pi. So in the pi direction, we have 4/3 here. So this is the other vertex. I already have my directrix here, right? So my ellipse is like this. Sorry, is like this, right? And the next thing that people do usually is they want another couple of points. To me, I think about it for a second. You know exactly where the center is. 1 more point for me is okay. 2 points is usually not enough for an ellipse. 3 points is usually enough. Okay, because given the 2 vertices here, you can find the center. So 3 points is usually as much as I want. Here they're going to use like a lot more points. Just this point for me is enough. Okay, and you know, you could have chosen, you see they choose like 2 pi over 3, 3 pi over 4, pi over 6, 5 pi over 6. You can choose like pi over 3, pi over 6, the more usual angles. But again, 1 extra point for me, so that you have a total of 3 is enough. So you'll see that they plot the points that they chose there. I would have done pi over 2 and I'd be good to go. Just plug in an extra point to get. Because there's also symmetry, right? If you have this point, then you also have this point just as a different r. Because you know this ellipse is symmetric because of the way we drew it. So having this point gives you an extra 4th point. But okay, just these 3, just to make sure, just these 3 is usually enough for me. Okay, that's it. That's what I want. That's how you graph given a polar equation. You have more examples, so I'll go over the initial part, finding the standard equation, and then we'll be good to go. So remember this. I want this to be a 1. As soon as I get that, to get that, I divide my equation by 4, top and bottom. So I divide by 4 here, I divide by 4 here. So that's a 2, and that's 4 divided by 4 is a 1. 4 divided by 4 is a 1. So now that I have a 1 here, I can easily see that the eccentricity is the thing multiplying the trig function, multiplying sine. So e equals to 1. So this is a parabola. When e equals to 1, when the eccentricity is 1, then this is a parabola. Again, don't confuse this e with the transcendental e for the exponential e to the x. Right? It's not the same e. This is a variable e, right? An unknown e, rather than the e that we know what it is, 2.7-ish, right? So then we find p, right? So EP is the numerator, is 2. So p equals to, so 1 times p equals to 2, right? So p equals to 2. So we clearly know e, we clearly know p. Let me go to the next slide. I've already done that. So E was 1, P was 2. So parabola. Already done it. What I can do more? What can I do? What else can I do about this? I see. Let me see what it is. I see. I'll do this here, and you can follow the rest of the example later. What matters to me is I know it's a parabola. I know it's sine here. So because this is sine, then the major axis is vertical. Remember, y in polar coordinates are sine theta, so sine means y. And because this is plus, that means the directrix is up. So if I were to graph, what I would do would be what would I do? Well, this is the focus. This is always the focus. And then the directrix is 2 units up. So this is the directrix. Y equals 2 is the directrix. So that means my parabola is like this, always moving away from my directrix. Right? So that's how my parabola looks like. Okay? As I've said before, I need like 3 points, so I would choose theta. I choose maybe these 3 points that seem easy to find. So I choose theta equals to pi over 2, 0, right? 0, theta equals to pi over 2, and theta equals to pi. So these are the 3 points that I choose. 3 are enough for conics in general. Okay? You see that they continue here. They have the same figure that I had. Wait, why is this pi over 2? Oh, right, whatever. So, oh, okay, the vertex. Yes, the vertex. Yeah, no, that's correct. Yeah, that's what I said, right? Pi over 2 here. It's pi over 2 here. Yeah, that's correct. Yeah, and then they get some 2 other points. You see that they use some weird points. I don't see any appeal on using these other than the ones that I described, so I'd rather use the other 2 points. Okay? Well, you can use whichever 2 points you want. I just want the vertex. I want this absolutely. And then 2 more. To me, those would be best, but you can use any other 2 points that you want. They even have 1 extra point. You don't really need 3 extra points. Just choose enough. Okay? Just really hammer that in. Last example that I'll do, this number here, I want it to be a 1, right? So I'll divide by 3. So dividing that by 3 gives me a 3 at the top. 1 minus 3 cosine theta. So I can easily see that the eccentricity equals to 3, right? So let me go back. So you got this here, right? Eccentricity equals to 3. And EP is the top of the equation after you got the 1 here, right? So EP is 3, so it means P is 1. Because E is 3, which is greater than 1, that's a hyperbola, right? And then let me sketch this here before moving on. If I were to sketch it. This is not my graph yet, this is just a sketch, so I know what to expect. This is a hyperbola. This is the focus. Always the focus. Let me do it in red actually. This is always the focus. Because this is cosine, then that means my hyperbola is horizontal. And because this is minus, the directrix is to the left. Okay? So P is 1, so it's 1 to the left. So that's x equals minus 1. Okay? This is 1 here, because P is 1. Remember, this is always P, right? The distance from the focus, from the center of your polar graph to the line, to the directrix, is always P. So that means my hyperbola is like this. Okay, so it's avoiding. And you have another branch here. Okay. So what I would do is I would choose theta for my graph, for my point plotting. I'd choose maybe theta equals to pi, right, to the left of the pole. I'd maybe choose 0 as well, because remember, when you point to the right and r is negative, then you get a point on the left. So that's a possibility here. So I get 0 just to make sure. Test these two, because maybe these two give me these 2 points here, right? Maybe I think they will give me these 2 points. But if they don't, then I can just move this distance to the left here to find the other vertex. It's fine. Okay, just make sure that the distance from the directrix to the vertex is the same. To the two vertices, right? Because there's 2 of them. And then I get, again, pi over 2, and then to get these 2 points, right? These points that I'll circle here. These are the 3 or 4 points that I'm looking for. So I'd get, for these extra points, I'd do pi over 2, and then 3 pi over 2. And once I have those 3 or 4 points, I'm done. Okay? You'll see that they'll follow their own process here. You'll see that they have the same expectation for the side. The directrix is the same. You'll see that they'll get 0 and pi, right? You can see that 0 and pi for the vertices. And you'll see that they get the values there. And as usual, they get like some random angles. You can do that if you want. Not my cup of tea. I just like choosing more directly. I would choose this and this. This and this, which would give me a lot better numbers, but it's up to you, really, what you choose. So that's it. That's all I wanted to go over. Once again, sorry that this is coming out a little late. Make sure that you practice doing this. There's an example, the last problem in the supplemental final review. That's there. Thank you for watching this, and I'll see you next time.